Welcome to the world of advanced aerospace propulsion. In this series we introduce the Hartman Penrose Lenticular Extractor or HPLE 10x7, a revolutionary lenticular saucer designed by Colonel James Edward Hartman. This vehicle is not just a conceptual leap, it's a new class of engineered craft that leverages Penrose-like energy extraction, synthetic ergoregions, and proprietary metamaterials. The HPLE 10x7's architecture enables cyclical energy splitting, where negative energy branches are absorbed internally and positive branches are converted into thrust. In this opening chapter, we'll set the stage with the foundational physics, authorship, and the bold vision behind this original invention. The HPLE 10x7 introduces the concept of a synthetic ergoregion, a zone engineered around the craft where effective particle trajectories are forced to co-rotate, mimicking the ergosphere of a black hole. This is achieved not by gravity, but by carefully designed electromagnetic, spin, and metamaterial structures in the hull. The synthetic metric near the craft is mathematically defined, allowing for precise control of time dilation and frame dragging effects. This engineered environment is the key to enabling Penrose-like energy extraction in a finite, terrestrial vehicle. The HPLE 10x7 is defined by its striking lenticular geometry, a saucer with a major diameter of 10 meters and a vertical thickness of 7 meters, including internal toroidal cavities. The vehicle is axially symmetric, providing an ideal platform for the formation of synthetic ergoregions and efficient energy flow. The internal structure is organized into 4 functional zones, each with a specific role in the propulsion cycle. This geometric envelope is not just for aesthetics, it's fundamental to the craft's advanced field dynamics. The core propulsion mechanism of the HPLE 10x7 is governed by the Hartman-Penrose extraction condition. E0 equals E plus plus E minus, with E minus 0 and E plus E0. This means that the injected energy splits into a negative branch which is absorbed and a positive branch which is amplified and used for thrust. The synthetic ergoregion is engineered so that these conditions are met, allowing the craft to draw from its internal rotational and field energy reservoirs. The HPLE 10x7's synthetic ergoregion is mathematically described by an effective metric, which governs the motion of excitations within the craft. The effective energy of a mode is given by EF equals gamma H E local minus LZ, where gamma H is a Lorentz-like factor, E local is the local energy, omega H is the engineered rotational field profile, and LZ is the angular momentum. The ergoregion is defined by the condition EF0, which is crucial for enabling Penrose-like energy extraction. Within the HPLE 10x7's engineered materials, effective mass can be tuned locally positive or negative through band structure engineering. Excitations in the synthetic ergoregion can thus exist as positive or negative mass modes. The positive branch MEF0 EF couples to vehicle motion, while the negative branch MEF0 EF is trapped and dissipated. This duality is a hallmark of advanced metamaterial physics and is central to the craft's propulsion. The HPLE 10x7's performance is made possible by 3 original metamaterials: HMSAF gamma, HTAL1, and HNISC alpha. Each is engineered for a specific function: boundary confinement, synthetic ergoregion hosting, and negative energy absorption, respectively. These materials are not adaptations of existing aerospace composites but are entirely new inventions, credited to Colonel Hartman. Their mathematical models and field coupling mechanisms are tailored to support Penrose-like dynamics in a finite craft. The Hartman magneto, spin ethafilm HMSAF gamma forms the outer hull of the HPLE 10x7. This metamaterial is engineered for high-spin electric coupling, supporting rotating field frames without mechanical spin. Its magnetoelectric tensor lambda-ij and boundary rotation vectors are tunable, enabling precise control over the synthetic ergoregion's boundary conditions. This film is a cornerstone of the craft's field manipulation capabilities. The Hartman toroidal etha, Lattice HTAL1 is embedded in Zone B, forming the synthetic ergoregion. This metamaterial features a toroidal band structure with engineered dispersion, allowing for the selective creation of positive and negative mass modes. Its high Q resonance at omega 0 and control over effective mass sign are essential for enabling Penrose-like energy extraction within the craft. The Hartman Negative-Inertia sync composite HNISC alpha is the core material in Zone C. It is designed with asymmetric damping, providing strong absorption for negative effective mass modes while remaining transparent to positive modes. Its complex effective mass with a large imaginary component ensures that negative energy branches are efficiently trapped and dissipated, maintaining the integrity of the propulsion cycle. Zone D's composite thrust coupling interface is responsible for converting the amplified positive energy branch into net thrust, It achieves this through directional field coupling and momentum transfer via stress-energy gradients. The interface is engineered for anisotropic emission, allowing for precise vector control of the thrust without moving parts, a major advancement over traditional propulsion systems. The HPLE 10x7 operates through a cyclical Penrose-like energy extraction process. Each cycle begins with the injection of energy E0 into the synthetic ergoregion. There, the excitation splits into a negative branch E-, which is absorbed in zone C, and a positive branch E+, which is directed through zone D to produce thrust. This cycle repeats at high frequency, with field asymmetry providing directional control. The result is a propulsion system that is both efficient and highly adaptable. Thrust in the HPLE 10x7 is generated by coupling the positive energy branch to anisotropic field emissions. The direction and magnitude of thrust are controlled by modulating field gradients in zone D, emission asymmetry, and the local refractive index profile. This allows for precise vector thrusting, enabling the craft to maneuver without mechanical gimbals or reaction mass, and making it suitable for a wide range of mission profiles. The efficiency of the HPLE 10x7's propulsion cycle is defined as eta HP equals E out minus EIN/EIN, where EIN is the energy injected per cycle and E out is the escaping amplified branch. Efficiency is tunable through the field rotation rate, material damping profile, and the band structure of the HTAL-1 metamaterial. This flexibility allows the craft to adapt its performance to different mission requirements and operational environments. The HPLE 10x7 is designed for a variety of mission profiles. In atmospheric test flights, the craft operates at altitudes from 0 to 30 km for durations of 5 to 20 minutes. The primary objective is to validate the formation of the synthetic ergoregion and demonstrate thrust vectoring capabilities. These tests are crucial for refining field control and verifying the performance of the metamaterial architecture under real-world conditions. For orbital insertion missions, the HPLE 10x7 operates at altitudes of 200 to 400 km, with flight durations of 1 to 2 hours. The goal is to demonstrate sustained Penrose-like thrust in microgravity, proving the viability of the propulsion system for space applications. These missions test the craft's ability to maintain stable ergoregion dynamics and efficient energy cycling beyond Earth's atmosphere. In deep space deployment scenarios, the HPLE 10x7 targets locations such as Lagrange points and lunar orbit, operating for weeks to months. The objective is to demonstrate long-duration propulsion using internal energy cycling, showcasing the craft's ability to adapt to variable gravitational gradients and external conditions. This flexibility positions the HPLE 10x7 as a candidate for future interplanetary missions. The HPLE 10x7's deployment infrastructure includes a launch cradle equipped with electromagnetic field stabilizers and injection synchronizers. The control interface allows real-time modulation of field parameters, while the power source is provided by compact fusion or high-density capacitor banks. This integrated system ensures safe, reliable, and precise activation of the craft's advanced propulsion cycle. To validate the HPLE 10x7's performance, a series of diagnostic objectives are established. These include confirming the formation of the synthetic ergoregion, detecting energy splitting into E+ and E- branches, verifying absorption of E- in zone C, measuring net thrust from E+ in zone D, and demonstrating repeatable cycle efficiency greater than unity. These metrics are essential for scientific verification and future development. A ring of diagnostic probes surrounds the HPLE 10x7 during experimental validation. Probe type A measures local energy density, Probe B measures angular momentum, Probe C tracks the synthetic rotation rate, and Probe D captures escaping field quanta. Together, these probes provide a comprehensive picture of the craft's internal dynamics and energy flows. Key observable metrics for validation include the synthetic ergoregion condition, EF0, detection of energy splitting E+, E0, E-0, and measurement of net thrust FHP. These are confirmed by comparing probe readings across radial bands, detecting escaping energy, and monitoring the absorption signature in Zone C. Successful validation requires all these signatures to be present and repeatable. High-fidelity simulations are used to replicate the HPLE 10x7's synthetic ergoregion formation, energy splitting, negative energy absorption, and thrust generation. The mathematical framework is based on the Hartman effective metric, with boundary conditions set by the metamaterial zones. Diagnostic outputs include energy density maps, angular momentum profiles, and thrust vector evolution, providing a virtual testbed for design optimization. The HPLE 10x7 is assembled in concentric layers, each independently tested before final integration. The launch cradle provides magnetic stabilization and field synchronization, while embedded sensors monitor the formation of the synthetic ergoregion. Operators control field parameters via real-time interface, ensuring safe and precise deployment across atmospheric, orbital, and deep space missions. 3 field modulation zones are defined for the HPLE 10x7, Zone Alpha for pre-launch stabilization, Zone Beta for active Ergoregion shaping, and Zone Gamma for thrust vector tuning. Each zone is controlled via embedded field coils and metamaterial feedback loops, allowing the craft to adapt its field configuration in real time for optimal performance in any environment. Simulation domains for the HPLE 10x7 are nested to capture the full complexity of the craft's field dynamics. Domain Alpha models the full synthetic metric tensor field, Domain Beta tracks mode propagation and energy splitting, and Domain Gamma focuses on thrust coupling and emission. Outputs include real-time maps of energy density, angular momentum, synthetic rotation rate, thrust vector evolution, and efficiency curves. The HPLE 10x7 is designed for adaptive deployment across atmospheric, orbital, and deep space environments. Each scenario requires dynamic tuning of field parameters, energy injection, and thrust asymmetry. The craft's metamaterial architecture allows real-time reconfiguration of effective mass profiles, band structure domains, and sink damping coefficients, ensuring optimal performance in any operational context. Field parameters in the HPLE 10x7 are dynamically tuned based on the operational environment. In the atmosphere, increased damping and enhanced hull confinement are prioritized. In orbit, balanced energy splitting and stable Ergoregion dynamics are maintained. In deep space, maximum extraction efficiency and long-duration cycling are emphasized. This adaptability is a direct result of the craft's advanced metamaterial design. Thrust vectors in the HPLE 10x7 are modulated by adjusting emission asymmetry, field gradient orientation, and energy injection timing. The control interface provides operators with real-time feedback, allowing for precise maneuvering and mission adaptability. This level of control is unprecedented in aerospace propulsion and is a testament to the craft's innovative architecture. Each deployment scenario for the HPLE 10x7 includes field overlay maps of synthetic rotation, spin-orbit tensor, and efficiency tracking. Diagnostic probe arrays are adapted to local conditions, ensuring accurate monitoring and control. These overlays provide a comprehensive view of the craft's operational state and enable rapid response to changing environmental factors. The HPLE 10x7's metamaterial architecture allows it to adapt to variable gravitational gradients, external electromagnetic interference, and thermal flux. Real-time reconfiguration of effective mass profiles and sink damping coefficients ensures that the craft maintains optimal performance, regardless of mission demands or environmental challenges. The Hartman-Penrose framework can be extended to include non-local field coupling, allowing distributed Ergoregion behavior and remote energy splitting synchronization. By introducing non-local coupling tensors into the synthetic metric, multiple saucers or modules can share field coherence, opening the door to coordinated multi-craft propulsion systems. The HPLE 10x7's synthetic Ergoregion can be generalized to higher dimensions, enabling multi-layered energy splitting and enhanced thrust via dimensional tunneling. By embedding a 4D Ergoregion manifold in a 5D effective space, new propulsion regimes become accessible, pushing the boundaries of current aerospace physics. Quantum entangled mode pairs can be injected into the HPLE 10x7's synthetic Ergoregion, enabling coherent thrust amplification and non-classical energy extraction. Entanglement allows for quantum feedback control of field parameters, further enhancing the craft's performance and opening new frontiers in propulsion physics. The Hartman-Penrose framework supports the development of multi-saucer arrays, where multiple HPLE units are linked via non-local field channels. This architecture enables shared Ergoregion envelopes and coordinated thrust vectoring, with the total force given by the sum of individual saucer thrusts plus intersaucer field tension. Such arrays represent the next step in advanced aerospace propulsion. Future extensions of the Hartman-Penrose framework propose new metamaterials such as HTAL X higher dimensional toroidal lattice, HNISC beta quantum damped sync composite, and HMSAF delta non-local spin orbit film. These materials are designed to support advanced Ergoregion behavior and quantum mode propagation, paving the way for next-generation propulsion systems. All theoretical constructs, material definitions, simulation protocols, and deployment architectures presented in the HPLE 10x7 framework are original inventions credited to Colonel James Edward Hartman. The framework is timestamped and documented, establishing priority for scientific recognition and future citation. This ensures that the legacy of the Hartman-Penrose architecture is preserved for future generations. The Hartman-Penrose framework is set to evolve into coordinated multicraft propulsion systems, quantum entangled thrust control, higher dimensional field architectures, and cinematic visual communication series. Its scientific impact includes introducing a new class of propulsion systems not reliant on reaction mass, a synthetic analog to Kerr ergospheres, and a reproducible framework for Penrose-like energy extraction in finite craft. All future publications, schematics, and simulations derived from the Hartman-Penrose framework bear the authorship seal, Hartman-Penrose architecture, original physics, original materials, original authorship. This seal is a mark of innovation and scientific leadership, ensuring that the contributions of Colonel James Edward Hartman are recognized and respected throughout the field. The HPLE 10x7 cinematic manuscript series consolidates the core contributions of each chapter: foundational physics, geometry and architecture, materials, applications, experimental validation, integration and deployment, simulation protocols, field deployment scenarios, theoretical extensions, and legacy. This comprehensive framework sets a new standard for advanced aerospace propulsion and scientific communication. As we conclude this journey through the Hartman-Penrose Lenticular Extractor, it's clear that the HPLE 10x7 represents a leap forward in aerospace science. By uniting original physics, advanced metamaterials, and visionary engineering, Colonel James Edward Hartman has laid the groundwork for a new era of propulsion. The legacy of this work will inspire future generations to push the boundaries of what's possible in science and technology.